Okay, so now we've seen what happens during the periods when a circuit becomes resonant, and X sub C and X sub L essentially cancel each other out, and the total impedance in the circuit becomes the value of the resistor. So let's take a look at a couple examples here of some RLC, some series RLC circuits. So for this simple circuit, we want to determine the impedance magnitude at the following resonant frequency. So at the resonant frequency, the impedance is, as I said before, equal to R. So Z is equal to R and is equal to that 10 ohm resistor. So to determine the impedance then above and below the resonant frequency, first we need to calculate and find the resonant frequency. So to do that, we use that relationship we just learned, 1 over 2 pi, the square root of LC. And if we insert our values for the inductor and our values for the capacitor, we get a resonant frequency of 5.03 kHz, so 5,000 hertz. So the next step then says for the circuit, determine the impedance magnitude at the 1,000 below resonant frequency mark. So at 1,000 below resonant frequency, the frequency and reactance are as follows. So from this, then we calculate the resonant frequency minus 1,000 hertz, and we get a value of 4.03 kHz. The As we said before, the resistance is that value of 10 ohms. So we need to calculate the capacitive reactance and the inductive reactance. So we just use the relationships that we've learned, 1 over 2 pi FC and 2 pi FL. And from that, we get 3.95 kilohertz, okay, almost 4,000, and 2.53 kilohertz. So therefore, the impedance at the resonant frequency below minus 1 kHz then is equal to, okay, we just apply our value here for calculating the phasor value. So R squared plus X sub L minus X sub C squared gives us a value of 1.42 k ohms. This is a more capacitive circuit then at that frequency. The next step then is calculating the magnitude at 1,000 above resonant frequency. So we do the same thing. We find out that 1,000 above 5.03 kHz is 6.03 kHz. Calculate again your values for X sub C and X sub L. So once we get those, 2.64 and 3.79 k ohms, we can put those into the relationship, calculate the impedance using the phasor resolution, the vector magnitude, we get 1.15 k ohms. So this circuit is more inductive. So if we look at what goes on here by looking at some relationships here, the waveforms, we can see the current and voltages in a series RL circuit as things relate to the resonant frequency. So in A, we're looking at uh, the current depiction. We get V sub S over R at some peak, then at the resonant frequency. The voltage relationships then, V sub R with respect to frequency, gives us a maximum then, as we've seen before, the source voltage at the resonant frequency. If we look at then the capacitor voltage, I times X sub C, at the resonant frequency, we have the maximum value of the voltage across the capacitor. Same thing for the voltage across the inductor. We can see at resonant frequency, we have the voltage rising and then it starts to taper off. And then finally, what happens then at the combination of the two, we can see at the resonant frequency, the voltage drops to zero. Okay, so keep in mind as we're working through your circuits what these diagrams are showing you. You might want to mark them in your book so that they're a reminder of what you should be seeing as you're making your measurements in the labs for resonant circuits. So at Series resonance frequency, the current maximum is equal to I max, the source, divided by the resistance. Above and below the resonance, the current decreases because the impedance is increasing. So let's do some quick solving here. Look at some example problems. Okay, in this case, you can see we've got X sub L and X sub C matched. So we would expect a resonance here. We've got 2.2 k ohms of resistance. So they want us to find the current in the circuit, the voltage drop across the resistor, the voltage drop across the capacitor at resonance. The resonant values of X sub L and X sub C then are shown in the diagram. So with that, we can calculate the current maximum, the source divided by the resistance, in this case 50 volts divided by 2.2 k ohms, which gives us 22.7 milliamps. Now, using our Ohm's law relationships, IR, IXL, IX sub C, we're able to calculate with the max current through the circuit and applying each of the impedance and resistance values, we can see that we have 50 volts, 22.7, and 22.7, as we would expect. So we notice that all of the source voltages drop across the resistor. Makes sense. V sub L and V sub C are equal in magnitude, but opposite in phase. This causes then the voltages to cancel, making the total reactive voltage 0. So if we look at waveform by waveform, below, in the first case, below the resonant frequency, in phase here at resonant frequency, above resonant frequency, and then our phase angle versus frequency. So at frequencies below resonance, where the capacitive reactance is greater than the inductive reactance, and the current leads the voltage source, okay, and we see that in this waveform, okay, the current is leading the voltage source. The phase angle decreases then as the frequency approaches the resonant value and is 0 at resonance. At frequencies above resonance, where the inductive reactance is greater than the capacitive reactance and the current lags the source voltage. Well, in the third diagram here, we can see just exactly that, where we have a lag between the source and the current, where in the lead you can see current leading the voltage. So as the frequency gets higher, the phase angle approaches 90 degrees, and we can see that in this plot then of the phase angle versus frequency. Okay, so we can see that we have a shift here that happens at the resonant frequency, minus 90, where the current leads the voltage. We reach a point of 0, and then as we continue, as the frequency increases, then the current lags the voltage. So as we move from 0 to some value of the maximum frequency or the resonant frequency and beyond, we can see what happens with the plot here. Later on, we're going to learn to do something called a Bode plot, where we're going to plot these frequency responses based upon frequency and different types of circuits. So in the next section, we'll come back and we'll talk about parallel circuits and as it applies to RLC networks.